Okay, so I just handed back the exam, and we have a few little conversations about that. And so now what we want to do is remember we postponed the assignment to write the finite state machine for the parser. We postponed that from today till tomorrow because we're going to go over some material now that shows, to give you some tips on how to do that. Now, you probably don't remember this, or maybe those of you who have tried the homework already do remember this. But at the end of class last time, or one of the things we did in class last time, was we did a demo, a big demo of code generation. And we had these two toy languages. One of the languages, the one that's shown on the left in figure 7.34 here, it has the input, and then on the right it has the output. And there's two sets of output. There is the object code and there is the program listing. And we said that what your next milestone for your translation project is to do the program listing and not the object code, right? So what we need to do is now we need to see what kind of statements. We need to sort of like note the different kinds of statements that we have. Now I can kind of like see three different kinds. There's one like set time 15, set time 15. That's one kind. Another kind is like abs time. And another kind is like stop. Yep. Okay. So let's just, and then for each one of these, there is a corresponding object code that uses this colon equals and without the parentheses and without, and the sets are the colon equals, and then the abs is the vertical bars and so on, right? So let's just remember what that is. Now from this, I think you can see what a typical token is going to be in this language. A token is going to be like an identifier. Here there's going to be a left paren, there's a comma, there's a right paren, there's these identifiers here. This is a decimal constant. Okay, so these are typical tokens in this language. Now, with this, starting now with this next milestone, the example here is not going to be as close to what you're doing. So you're going to have some design decisions to make that you're going to be on your own. It's going to be a little bit more open-ended than the previous milestone. Okay, so let's do here, and then we saw in figure 7.34, this other part of the figure, how the error handling is handled. So, and then here we did the GUI stuff, and well, actually we didn't do any of the code, did we? So here, let me go over this. 7.35, blah blah blah. Okay, there's the dialog box stuff. Lay it out. La da 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 da. Now, you guys, here's one big difference between the way this translation program works and the previous one. With this one, none of the logic is in action performed. The only thing action performed does for this program now is it sets up the input buffer. So it does end buffer gets new, end buffer text area get text, just like before. And then it does translator, tr gets new translator, and the translator passes a pointer to a reference to the end buffer, and then it just calls one method called translate. All right. So now I think before there was some logic that we did. There was a loop, I think, maybe in the action performed. But now this translation, that's the model. So you don't have to change that at all. That'll be just like what your next project is. Now, you guys, this next figure is a UML diagram. Now let's come back over here. Check this out. Each one of these in parentheses in this language is called an argument. Okay? Now look, there's two kinds of arguments. This kind of an argument is a what? Identifier. It's an identifier argument, and this one is an integer argument. Okay? So, using our standard technique of polymorphic dispatch, what we're going to have is an abstract argument, And that abstract argument is going to have two concrete arguments, an identifier argument and an integer argument. And we can see here from the UML diagram that the one thing that each one of these that every argument does, it has a method that's called what? Generate code. And that generate code returns what type? String. Yeah?
Okay.
So now, why is oh, and then let's take a look at the attributes. So the ident arg has a string value, and the int arg has an int value. Okay? So that's they store. So in this case, the string value would be time, the string time, and here the int value would be the integer value 15. Right? And then they have these constructors that just set their attributes to whatever the caller is, gives them. Okay, so now what is this generate code going to do? Well, for an argument, let's go back to the code. Let's go back to the input output. You see, the output here is you see the output for abs time. The output for abs time. What does that get translated to? See here, if you say if the source code is abs parentheses time, then the object code is time colon equals time gets vertical bar time vertical bar, right? Now, what is this? So now, what is this time? What is this time? This time is a what? I mean, here, what is this time? This time is
an arg?
Yes, it's an arg. This is an ident arg. So what will times generate code do? It will just print out this time here and this time here. See? That's all it will do. Because this is the code that gets generated. Okay, so it's just printing it out. Right? That's what it will return. Okay, does everybody see how that works and the concept of an abstract argument? Okay, so here's the Java code for that. It's pretty easy. Abstract public string generate code for abstract public class arg, and there's the ident value. Any questions there? That looks all very okay. And here's the same thing for int. Okay, so we've seen Java code like that before. Now, this next one is the UML diagram for a token. And here again, I think we can go over this pretty quickly because our token class is just like our token class for our own project, for our own, PEP 8 assembly language. But now the tokens, but now what are the tokens here? Like we said before, the tokens are, we have an identifier token, like set and time would both be identifier tokens. Integer, that'd be like the 15. Then we have a t comma, and then we have a t left paren and t right paren that correspond to these, and then we have an empty and an invalid. So are we good? So that's all just like we had before. Very similar. Is everybody clear on that? And so here's the Java code for the identifier, for the tokens, abstract token, so the abstract public class A token. And then, so here's the one for the identifier token, extends A token, here's the integer, here's the comma, there's the left paren, there's the right paren, there's the empty, there's the invalid. Any questions there? All that's just like what we had done before, like what you've done before with the tokens, right? Now comes a crucial concept. And that is, what we have here on figure 7.40 is a diagram of
instructions.
Of code. This is a diagram of the code. Now, because you see, look, let's go back to this example. Here's an example of code. Are you with me? This is an example of some code, right? And here's some example of some code, and here's here's another example of code. So they have different formats, right? Different statements in the language have different formats. Are you with me? So what we need is we need a class that can collect all the information that is contained in a statement in that language. All the essential information, so that it can reproduce, so that it can either A, reproduce the program listing line, are you with me? Or B, do what? Actually generate the object code. Are you with me? So here's the whole idea is that as you parse, now we're talking about the parser now. As you parse a line, at the end of that line, the result that you should have is you should have an object of static type A code which has one of these formats that has all the information in there. Do you see what I mean? To store it, because what you want to do is you want to go all the way through the program. When you get all the way through the end of the program, you'll have a list of code objects. You'll have a list of code objects, and inside that code object will be all the information that you need to either reproduce the line in the listing, the program listing, or actually generate a line of code. And what you'll do for your project is, this next project is the thing that you'll generate will be the program listing. Okay? So now let's take a look at how this is all structured. So check it out. So what does A code stand for? Abstract code. And what does abstract code, what two methods does every abstract code record have to do?
Generate listing.
Yes. Generate code and generate listing. And what are their types? What do they return? Strings. Because that's all translation is from one string to another string. That's all translation ever is, in any language. Because we deal with character, we deal with alphabets, and it's just a string in one alphabet, string to another one.
So you're saying that part of our project for next time is to generate just the listing?
Yeah, but what you should do is you should go ahead and set up the generate code method and just leave it blank. Or
so then the next step after that would just
yeah, and then you'll see when we get to the main program, or when we get to the translator, you'll see where it calls the generate code. You can just not call the generate code. You can just do the listing part. Are you with me? Now I'll tell you right now that the parsing part, our language is so simple that usually the generate code is the hardest part, but in this project it's easy. It's going to be easy. The parser is going to, once you get the parser done, you'll be surprised at how easy the code generation is.
It's kind of one-to-one with the binary.
Yeah. So this is it's a very simple. It's not like compiling from a HOL6 language. Okay. So so everyone understands the abstract code. So now look, what is a subclass of the abstract? How many specific code types are there?
5.
5. Error, empty instruction, unary instruction, 1 arg instruction, and 2 arg instruction.
This is for these.
And that corresponds to these. Are you with me? Okay? So this is a 2 arg instruction, this is a 1 arg instruction, and this is a unary instruction. Are we good? Now be thinking ahead. What kinds of assembly language statements are you going to be parsing?
Unary, non-unary.
And dot commands.
And dot commands.
Now, so can you see, okay, how, and is everybody with me on this? So what you need to be thinking ahead of is, how many different things do I have? And furthermore, what is the format of what comes, when you have a unary instruction, what does it consist of? When you have a non-unary instruction, what does it consist of? When you have a dot command, what does it consist of? Are you with me? So you'll have to do this accordingly. You have to figure that's your design decision those are your design decisions. Okay, but let's see how this one does it for this particular language. So what we have is empty. Not empty. Error. So now what does an error have?
the error message.
The tokenizer recognized a token that doesn't exist.
Well, I mean, for whatever.
T invalid.
T and L.
Yeah, either T invalid, or it could have been a valid one, but it was expecting something else.
Right.
Okay.
But whatever it is, whenever an error occurs on that line, what do you suppose that string, that error message string, that's going to be the string that you want to print out for the, we saw those error messages.
Good error messages.
Yeah, you want good error messages. So that's where you put those in the attribute of the error code object. Are you with me?
Okay.
Okay.
So if we encounter an error, we'll say.
Encounter an error, then you generate an error. What you do is you generate that for your code, and that code goes in that line, in that line, and then that will be your. And you put the error. You decide what the. How,
Okay.
yeah. Okay.
Sure.
And then empty instruction. That's just if a user puts a blank line. You want to allow the user to have blank lines in the source code. Are you with me? Okay. Unary instruction. That's like this. So what does it need? It only needs what? A mnemonic. So what are going to be the mnemonics in this language?
Stop.
Set, abs, stop.
Oh, right.
Those are the mnemonics, right? Those correspond to our mnemonics. Are you with me? And so all it needs is the mnemonic, right? And then what about one arg instruction? What will a one arg instruction have?
One arg.
Well, yeah, so here, one argument. So what will it have? No, the first thing it'll have is a what? What's its first attribute? A mnemonic. So in this one, what is the mnemonic?
Yeah.
It'll be the abs. Now this won't be a string. This is going to be an enum.
Right.
Are you with me? So it'll be an enum. That's the abs, and then the arg, and then now what's the other one it has?
Abstract arg.
Yeah, and that's arg. A arg, And that's an abstract arg, and that's going to be this, right? And then, but then what do we already saw what an argument has. What does an argument have? There's repeated there, right? Are you with me? So, is everybody clear? So arg has a generate code and da-da-da-da. So we looked at that. We looked at what
we just saw that. Okay.
we just saw that, okay? But and then what does a two arg instruction have? Here, there's two arg. What does it have? It has a mnemonic. So here in this case, set, and then what?
First arg.
A first arg and a second arg. Now don't call them args. I mean, whenever you're going to be doing this for our PEP8 assembly language.
We call them operands.
Yeah, we don't call them args. We call them operands and operand yeah. So don't just blindly take this terminology and okay. So think about how you. Okay, and the difference between a two arg instruction is it has a first arg and a second arg, whereas the other one just had an abstract arg. It just had an a arg.
Right.
Are we good? Does everybody see how that works? Okay. And furthermore, when the A code calls generate listing, for that one, like if you want to generate the listing for this one right here, what it will do is the two arg instruction will return the proper string so that it will look like this, and it will call what? The generate code for this and this. You see, and then it will put them together and it will generate, and actually it will. Well, for the generate code, it won't. For the listing, it'll do it like this. But for the generate code, it would do it with, time colon equals time plus 50. Yeah. Or time colon equals 15, I guess. Yeah. Okay. So does everybody see how that works? Now the rest of the stuff that's coming up now is I think we can go through pretty quickly because it is just the Java for that UML diagram that we just saw. So are you with me on this? So abstract public class A code. So we have generate code and generate listing. And then here's the error class, the specific error class. And what does it have? It has a constructor. And what does the constructor do? Yeah, we give it the error message when we construct it, and it sets its attribute to that. And what does it do for the generate listing? What does it return? Nothing, because if there's an error, we're not going to ever generate a listing anyway, right? So we just We have to return something, so we just return the empty string. Otherwise, what do we return? The error message, okay?
Wait, so we generate the error message only when we're trying to generate code?
Only on the listing. We don't ever generate code if there's an error anywhere. So what you're going to have to do is you're going to have to go all the way through the program.
How come we return error message when we call generate code?
Sorry, it was the other way around. Yeah, sorry, it was the other way around.
If we did listing and we have an error, we wouldn't know really. It just wouldn't be.
Well, we would say, remember how we did this? How this one was designed? We said line 6, error message, blah blah. Remember, so we'll keep track of the line and yeah. Okay, and then here is the empty. Well, of course, the empty string on the generate listing. What do we return? A new line. Okay.
Okay.
But do we ever generate code? We don't know. It doesn't generate code. Now, does everybody see that? Are you with me with that there? Yeah? Okay. And now here's the unary instruction. So the unary instruction corresponds to like this stop, right? So what does it have? It has
Well, it has
a private attribute named mnemonic, and that has an enumerated mnemon.
Is that it?
And the
Is that a type mnemon?
No, that's our type. There's a file mnemon. There's a file that
Class.
there's a class. Yeah. Enumerateds in Java are classes.
Right.
Yeah, so they're not
Okay. Looks
they're not
our
like
state-
integers.
Like our state class is the.
It is enumerated. Yes. And you'll have an enumerated. Each one of these has an enumerated, right? Okay, and then and look what generate listing does for this. It returns maps dot what? Mnemon string table dot get mnemonic. So that it generated the stop and then the new line. So what it did is it looked up the mnemonic, the enumerated stop, and remember how we had the map demo? And we had the string, remember we had the string table, we had the mnemon tables. Remember one went from the mnemonic to the string and the other one did what? Went from the string to the mnemonic. Remember? So this one's going from the mnemonic to the string so that you can print this out. Is everybody with me on this?
And that's how we do if you have if it was capital S, lowercase t, capital.
Right. What we will store in the table is the case the way we want it to be done in the listing. Yeah? Are you with me? And now look, I mean, we're not going to see the generate code, what calls it, but let's take a look at the code for generate code here. What do we do?
Switch on mnemonic.
Switch on mnemonic, and then what?
2 cases? 3 cases?
3 cases. The last case should never occur, but what? If the mnemonic is what? M stop.
Stop.
We return stop, yeah.
And if it's MN, return nothing.
Right. Okay. And then and the default should not occur. That's you should always put a default in your switch statements, but that should never occur if we've coded it correctly.
Would this work correctly if you didn't have a case MN and just had default return nothing?
Ask it again.
Would this work if you didn't have case on MN and just had default return nothing? So, you know.
What do you mean?
What do you mean? Well, you have to have a default. Default is a switch keyword.
Right.
So I don't understand your question.
I guess.
So you would have to switch on
what does
mnemonic.
default actually do?
Oh, sorry. Oh yeah, you should actually know this. No, I mean we should.
If you go
No. Wait. Yes, the way the default case works in any switch statement is if none of the above, if it
gets them all and none of them.
was, then it does the default.
So my question was, could we technically get rid of case M sub end? So if it'll check case.
Oh, I see. So we could have said default return empty string. Yeah, but it would not have been as
It would be hard
what I'm saying readable. I mean, it would not have been as documenting. This is better self-documentation of the code.
Sure.
But you're right. We
And in
could.
general, we don't want defaults to ever.
Well, I mean,
Or
In this project, in this project, there will be a couple more like this. But in general, sometimes sometimes you do want defaults, and they occur, and you expect them to occur, and then you do that. I'm surprised we haven't run across that yet. But because that's both, it's like that in C++ as well.
Right. I think it might have been a couple years ago.
Okay. So now here's the one-arg instruction. So what does the one-arg instruction have? Okay, it's got the mnemonic, and then it has the abstract arg. Are you with me? And then the constructor just sets them to what we give it, the attributes. Are you with me? Just like all these constructors do. And now what does this generate listing do? What does it do? It returns what? Now check this out. What does it do? This is for generate listing. Now see, that here it's got to return abs time for the listing. Are you with me? It's got to return abs parentheses times. If abs is the... So can you read there how it does that?
Yeah, it has two strings
Two strings, yes.
and an end line.
Yes.
The first string is the mnemonic.
Is the mnemonic, and the second string is the what's in the parentheses.
Right, the argument.
So you see that paren s?
Oh, it prints the parentheses itself. Oh, okay.
It
has another string that has what's inside.
Yeah, and so do you see that that's exactly the same format as this? Abs, space, paren, arg, this.
Okay.
Are we good? So that's how that listing. So this is the kind of thing you'll have to do for your listing.
Do we want to generate code for those?
Not this time.
We're just doing the listing.
Yeah, the next one is the code.
No, go back. When we're doing returning those strings, the second argument is generate code.
Oh yeah, see that's because, well no, that's because the only thing these arguments can generate are code.
Oh, that's right.
See, because it's going to be the same time, whether it's time here or whether it's time here,
Right.
it's going to be the same thing, so
Okay. Yeah.
I could have done generate code and generate listing, but then they would have done the same thing.
Okay, yeah.
But you're right, that's a little confusing, isn't it?
Self-document.
Yeah, you're right. It might have been better to self-document it to have it there. Yeah, that's a good point. That's a design decision that maybe I should reconsider, huh?
Could be.
Are we good? And here's how we generate the code. Does everybody see how? Sorry. Yes.
Yeah.
Wait, is that what we're doing?
Maybe it's
Well,
the next
change the
page.
page.
I forgot to change. Yeah.
There we go.
So here's how we generate the code. So now which ones? There's only two instructions that are like that have this format.
Absolutely.
ABS.
Abs and neg.
Okay.
So do you see how it generates the code? Is that cool? I think that's so slick. So you see, the way you generates code is %s. So that's the
So it just says it in the order that you put it.
in the order that you put it, and then after the double quotes, that's the format string, and then comma, and then we look up the arg, the first, the arg generate code, and then the arg generate code, because what this does is time gets here. It's like this: time gets vertical bar time this.
But the generate code is still outputting, in this case, time.
Yes.
the string.
That's what we said. That's what we said a minute ago. Yeah, time. Remember. Yeah. I didn't bother to. Maybe I should have put a generate listing, but it would have done the same.
They would both output or return time, right? The code and the listing both.
Well, I mean, all I would do is I would be calling generate code here, but in the previous one I would be calling generate listing, but it would do the same thing, so I didn't bother.
That's fair.
But anyway, does everybody see how this and how the negative works? It puts out. See how the string for case m neg?
Yes.
It's hyphen.
Yes.
Okay, gets hyphen and then it's. See how this is why this format
String not format.
works. It's so flexible. It's amazing. Those guys who did C way back, decades ago. I mean, they had this system, this string format system thing that works just really well. And so it's the same thing with these two args. Okay?
More cases.
And more cases. I think you can. I think you can get that out. Are you with me? Look at how this is. This the generate code? See how the m add is s plus blah blah blah, and now that we have a first arg generate code and then a first arg generate and the second arg generate code, because that would be like, So if you said add time 50, that would be time gets time plus, and so yeah? Are we good? And now here's the lexical state.
That's the third part, right?
The lexical state is, let's not go over this because this is exactly like, this is just the tokenizer.
Okay.
Oh, okay.
All right, so the tokenizer, this is just the buffer, and you back up the input
Yeah.
and blah, blah, blah. So we've done all this kind of stuff before, right? And now what we want to really talk about is what you have to hand in on paper
Yeah.
for tomorrow. Now, this figure, 7.43, this is modified from what's in the book, so go by this.
I trust you.
No, sorry. Oh, yeah, this is modified from what's, so go by this. Now here, this is really, I want to point out some very crucial feature of this. The first crucial feature to understand about this is that there is one state called PS finish. Now PS stands for
Parser state.
parser state. And because what happens is, as you scan tokens, over here, as you scan tokens, you go boom, 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 boom. The very last token that you scan at the end of the line is the what?
Empty?
Is the empty token. That's always the token that you scan at the end of the line. That means that your final, your PS finish,
No matter what is empty.
no matter what, you have to have a transition on T empty to that.
Okay.
So that's rule number 1. Okay? Rule number 2 is you need to make a list of all the tokens, which you already have. You've already done your token, right?
From the tokenizer?
From your tokenizer project.
Okay.
And every single transition on this has to be on one of those tokens.
Okay.
Are you with me?
All of these transitions? Or will
Every transition on this figure 7.43 is a transition on a token from the lexical, that it gets from the lexical analyzer.
Yeah, we do. Because
so like right paren would be...
In this example, in this language, right paren is a
Okay.
token. In
Our
this
home
language,
nothing isn't this.
no, it's not. What I'm saying is you have to design your own. This is an example with this language of what you have to do,
Tokens are transitions.
and your tokens from your lexical analyzer are the transitions.
Okay. And we have to decide what our states have.
And you have to decide what the states are and what the transitions are. But my point is, the point is that rule number 2 is that every transition on this finite state machine must be on one of those tokens that you've already, that your tokenizer will give you.
Right.
Are you with me? Now, let's go through and let's go through this finite state machine, and let's imagine that we are scanning this. All right? Now, what is the output of the lexical analyzer? A stream of what? A stream of tokens. And what's the input for the parser? A stream of tokens.
So we have tokens.
So imagine, now that we're scanning this, we're not scanning SET.
We're scanning.
The tokenizer did that. So what would we get if we start in the start state, and if we're right here, and our parser is scanning this, what token is it going to get?
Identifier.
It's going to get an identifier. So look up here at the start state, PS start.
Identifier only
An identifier, but wait a minute, there's 2 things on an identifier.
Are those technically 2 different tokens?
Yeah, now let's see, okay. So now let's see what happens. Actually, there's 2 on an identifier, and there's one on T empty.
At this point.
There's one on T empty.
Because do we need to be specifying like you
There
did
is one on
here?
T empty.
There is one on T empty. So, and when we start at PS start, there's one on T identifier at the top that goes to the right, one on T identifier that goes down, and then there's a T empty that goes to PS finish. Now the T empty one would be what would happen if you're starting at a blank line, an empty line. Are you with me?
Loop on start?
Go down.
No. The looping, oh yeah, that's a good question. The looping on the spaces, all that was taken care of with the tokenizer.
Yeah.
So you don't loop on space. All those spaces were taken care of with the tokenizer.
But this reads new lines, right?
This reads one token.
That token is
A group of terminal characters that have meaning as a group. A string of terminal characters that have meaning as a group.
Okay. So if this gets empty from start,
So if it gets empty from start, what that means, the only way that can happen is if you had a blank line.
just a blank line. Okay.
In which case you will know that will be
And
the,
if you had another blank line, then it would just do that
Just do it
again.
it would just do it again. But that would mean you'd have two blank lines. But, and if the user can do
That's
that,
fine.
and not only that, but even if the user has a bunch of spaces here,
But that'll get.
that will still just be one new line. That will just be one empty, because those leading spaces will be consumed by the
Yeah.
lexical analyzer.
Okay.
Are we good? Oh, you guys are with me on this, I can tell. So now how do we distinguish between the T identifier going to the right and the T identifier going down? What we have is we have notes at the bottom. Okay?
fine.
And that's T identifier, superscript 1. You go down here, note 1, and what does it say on note 1?
Only stop and end.
Only the identifiers stop and end take you to the PS unary.
So do we need to have these?
In
buttons?
our parser, can
In
we
your
say just these tokens.
Yes, what you're going to do is you're going to code that.
Okay.
So what will happen is the parser will get an identifier. It will look up that identifier in the map,
And we can say
and it will, and the logic, it's a direct code technique. By that logic, if it finds the stop and end, it will go this way. Otherwise, it will go, and then add, sub, mul, div, neg, and apps, it'll go this way. So you need to do the same kind of thing in your thing here.
So if on here we had said, we hadn't done that note, and we had said start goes just on an identifier, let's say,
But you might want to go to something depending on if it's
yeah.
unary,
I'm wondering
unary or
why.
not, yeah.
So you just went to one.
And not only that, but you can have a dot command.
Here, this-
Not only that, but you got to worry about dot
If
commands.
we did,
Are
we did
documents,
stop and then did a hexadecimal constant, that would
are
be
they
wrong.
tokened as
So we
identifiers?
might need to set it up like that.
No, they're documents.
They are dot commands. It knows because it scanned the dot.
Scans the dot, goes this.
Because it
Yeah,
would
yeah.
give it the
Okay.
option here, but if it was stop and then a decimal constant.
But some
that would
dot
be wrong.
commands don't have
Yeah.
operands and other ones do.
That's right.
Yeah.
That's right. That is right.
So, if
That is right. In fact, I would, yes. As a matter of fact, I have a, based on lots of experience here, I would have a, well, I'll let you grapple with it.
if our finite state machine would allow maybe like, let's say stop and then a hexadecimal constant after that, that's incorrect.
That is
We need
incorrect.
We need to make sure our finite state machine
That
won't
is,
let that happen.
that is correct.
Okay, so that's fine.
So like if this, like here, if you did this, this is wrong. Here, if somebody said this, stop parentheses, time.
Oh, that's horrible.
Well, I mean, no, this is an error. This has to be an
That's why
error.
it's split up like
That's why
that.
there's,
That's why it's split up like that.
because we wanted to make them one.
Because you want, yeah, you don't,
Oh,
you see, that's why you have to split it up, because this has a different format,
Yeah.
right?
Bigger reason.
Yeah.
Are we
Okay, so let's work on through.
Yeah.
Okay, and then after it does that,
Gets
you know,
identified.
either add, sub, mul, div, neg, and add, are you with me? After it does that, then it's in this called PS function state. And what does it expect next?
to have a left
It has to have a left paren. And then what does it expect?
It has to have-
an identifier. Notice it can't have a number.
Because it has to be an identifier.
Yeah, it has to be an identifier, right?
Unary, single operand, yeah.
And then, once it gets that identifier, it assumes that's an argument.
Right.
At that point, it knows that that's an, and then what does it do? Well,
Either-
a T right paren, but note 3 what?
Only mnemonics, negative.
Neg and apps, and 4
So we can say.
and comma only if it's these others. So you specify exactly which ones that it takes to do which
If
one.
we read in a right paren, then we check if our identifier was abs or
Yes.
Neg.
And otherwise you'll generate an error.
Yeah.
Yeah.
okay.
Are we good? And then after that comma, what is after the comma? What does it expect?
identifier.
Either an identifier or an integer, in which case second operand, and then a right paren and then empty.
Yeah. Okay.
Yeah? So now I think you should be able, now, here's the thing. You have to know the rule, you have to know what makes a legal PEP8 assembly language instruction and design your finite state machine accordingly. Are we good?
So So for tomorrow, we just have to turn.
For tomorrow, you turn this in on paper.
Just our financing machine.
Yes. And we'll probably have some more questions tomorrow morning.
So what we
Or I mean,
need-
tomorrow at the beginning of
Why does
class.
the problem cause to draw the state transition diagram for the F? Yeah, the problem was confusing.
Well, the problem is to do this for the parser.
Does it matter what we name our states then?
Well, you should name them something. I tried to name them
Something.
something that was indicative of where you are,
What's a
what.
parser?
I tried to name them, I tried to make them meaningful.
Or? Okay.
Like this is PS non-unary 1,
So like, because we have an.
PS non-unary
If we
2.
read an identifier, we know it's, okay, it's a function. Then we read a print, we're like, okay, we just open the parentheses.
Yeah,
Well,
Or
yeah.
another identifier.
Yeah, so try to name your, try to make meaningful names for your states.
Even though it's going to be different.
Well, actually, I'll tell you what, I mean, you don't even actually really need names for the states here, but you're going to need them. You might as well put it, you might as well think about it because you're going to need them for your code.
Okay.
Yeah, because they will be enums.
So is the financing machine that we're gonna make, is it look similar to this, or is it for the tokenizer that we already made?
It is with the token.
It is with the tokenizer that you already made, and every transition on your finite state machine for the parser has to be on one of those tokens that you've already, that you already have a list of from your,
Right. And so the parse that we're making is from the program that you have on there.
the parser
Files.
we're making is not from this example. The parser we're making is to translate a PEP 8 assembly language program. So you have to understand what the rules are. By now, you've written PEP 8 assembly language.
You have to understand.
So you have to understand what comes next, you know. Are you with me?
I was just wondering, because there's so many PEP8 commands.
Well, there's only a
We only do
subset.
certain.
You only have, yeah, you're not doing the whole
Have we
thing.
taken care of the symbol problem yet?
Okay, that's a good question. Fortunately for you,
No symbol.
this
We don't
project
have symbols.
is not going to have symbols. But I will say that people and the students in the past have actually implemented a symbol table and have done it. And it raises an interesting issue of how you organize the translation process, because you have to go through and collect all the
The
symbols.
symbols would be, yeah.
And then-
They would be tokenized as just identifiers.
Yeah, and because, yeah, it's used here, you got issues of, if you define it here, I mean, if you use it here, but it's not been defined anywhere else, then it can be defined after where you use it.
I would probably put it as a new token.
So
Well,
That'd be appropriate.
I mean, I think after you get this done, if you have a little time left over, you might want to
look at it.
look at that problem, at doing that. And because there's some interesting issues, translation issues that crop up. Okay? Good deal. I'll see you tomorrow.